Hello everyone. We're now going to dive into the meat of our fourth unit, which is on sorting. Now sorting is not really like a data structures thing per se, it's more of an algorithms thing, but it will contextualize some of the data structures that we're going to go over in the trees unit. So it's important to go through both because it's algorithms and also because it helps to understand the point behind some of the tree data structures we're doing. Now, before I talk about efficient sorting algorithms, I want to talk about sort of the least efficient sorting algorithm you could possibly come up with, because that also establishes a baseline of complexity and allows us to talk about some interesting complexity relations. And this will be the first factorial algorithm that we see in the course. So what we're going to do is check all permutations of an input and see which one it happens to be sorted. So as an example, if I have an array which has elements A, B, and C, that means I'm going to have to check A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, and C, B, A. So in particular, given an array with n elements, there are n factorial possible permutations to check. So the algorithm to do this, to enumerate all permutations, would choose one out of n elements for the first one. Then it would choose one out of the remaining n minus 1 elements for the second one, and so on and so forth. So you can see that this would take, this would take n times n minus 1 times n minus 2 dot 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 until we choose our last element if there's only one left. So that's how you see that there are n factorial possible permutations. So first, let me just write some code to enumerate all the permutations. And actually, recursion is our best friend here, because what we're going to do is pick the first element, then keep going and pick the second element. But that'll depend on what choice we made for the first element. So let me just say def perm array. And I'll also have an index which says which element is it that we're choosing. Are we choosing the element in index 1, index 2, index 3, and so on and so forth. So my stopping condition is if I'm looking at if I happen to have reached the last index, then I'm going to go ahead and print what's in the array, because I've gone through and I've made all my choices. Otherwise, I do have to loop through and make my choice at this particular index. Okay. So let me actually write some comments here to be a little more specific. So array is a list. This is a list that we're permuting in place. So we're only going to pass one list around. We're going to be swapping elements within this list. And when we get to the end, so this says which element are we choosing, or what is the index of the element we are choosing in the array. Okay. So if we haven't reached the end, we need to make a choice, and then we're going to need to do some recursion. So I'm going to need to move things around the array. You know, when I started with ABC, you can see that at some point I swapped, you know, A was the first element, but in some other possibilities I swapped in B for the first element. So I flipped A and B. And then I swapped in C for the first element. So I'm also going to have to make a method, which is going to be very helpful in all of our sorting techniques, to swap two indices. So I'll swap indices I and J. So this is the standard thing where you remember what's at the array at index j, and you'll say that the array at index j then becomes what the array at index I was. That overwrites what was array at index j, but we remembered it in our temp variable. So we can just say array at index I is equal to temp, and that'll do it. That's an in-place swap. All right, so here's what we're going to do. We're going to assume, so this is a recursive method. We're going to assume that everything before IDX is fixed. But we want to take something that's after IDX and swap it into IDX and keep going. So those are the steps. So what I'll say is for I in range IDX length of array. So I'll start at this index and I'll say swap array I index. So I'm going to swap in whatever index is for the ith element. And then I'm going to recurse. I'm going to say perm array IDX plus 1. So I've chosen what is going to go into index IDX. It's one of the I elements that's IDX and after. Now I'm going to do the recursion. When I'm done, I'm going to swap it back and try something else. All right. So swap in array I for array index. Keep going recursively to figure out array at index is 1. And then swap back and try something else. Okay. So that's the code to do all of our permutations. So it's going to print every time it gets to the end, and it's made all of its choices, it's going to print. So just to show you, if I say perm 0, 1, 2, 3, just as an example, this will print out all, actually 24 permutations. So we have n factorial, so n here is 4. 4 times 3 times 2 times 1, that's 24. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You can see that that's 24. And here they all are. Actually, let me do a smaller number. I know this is only going to be 6. Do we get them? 0, 1, 2, 0, 2, 1, 1, 0, 2, 1. Actually, let me make these, just so we can put it in correspondence with what I had up here. I'll make this A, B, and C. Okay, so we have ABC, ACB, BAC, BCA, CAB, and CBA. They didn't come out in exactly the same order, but that's basically it. Okay. All right, so now we've enumerated all permutations. So you see, this is kind of cool. I mean, I don't know, personally, I feel like it's not obvious how you would do that. But once you kind of sit and break it down recursively and say, okay, you know what? I'm going to fix one index at a time and then branch out and try all possibilities that happen after that. This is a natural thing for recursion. And this will enumerate all the possibilities. So I'm going to have you do a quick exercise where you use this to sort. So it's going to enumerate all the permutations. And you're just going to make a method. You're going to fill in a method that checks to see, hey, is this permutation that I'm trying actually sorted? If it is, then we'll return that, and that'll be the sorted version of the array. Okay, so you can go do that real quick, and then we'll analyze the complexity.